to make semiconductor materials conductive. As discussed so far this week, we need to excite electrons from the valence band to the conduction band to make semiconductors more conductive. This can be achieved in using several different routes. The learning objectives of the upcoming 3 videos is to understand these 3 routes. First, we excite charge carriers using thermal energy. Another option is to get help from impurities in the semiconductor material. This is what we call doping. And the third option to be discussed, and very important to solar cells, is to use the energy in the light to excite electrons from the valence band to the conduction band. Before I will discuss these various routes to excite charge carriers, I will first discuss the concept of the Fermi level. Let's consider a metal. Electrons are filling the electronic band of a metal. The electronic band and its bandwidth with continuous levels. This band is not fully filled by electrons. The probability to find an electron is not the same at all energy levels. At low levels, you will have a probability of 100% that electrons will fill this level. Well, at high levels, this probability is close to 0. The probability to find an electron can be expressed by the Fermi-Dirac distribution function. This function reflects the probability that an electron will occupy a state having an energy E. Low in the valence band, this function is equal to 1, whereas high in the conduction band, this value is equal to 0. Note that this equation is only valid for a material that is at thermal equilibrium, which means that no additional energy is coupled into the system by electric biasing or light absorption or heat conductivity. The Fermi level represents the energy level at which the electrons have a 50% chance to occupy the energy level at any given time. For a metal, it is easy to see where the Fermi level is positioned. Physicists use in general the term Fermi level. Chemists might use a different term. They might call this level the total chemical potential of an electron. The shape of the Fermi-Dirac distribution does change with temperature. At absolute zero, so a temperature of 0 Kelvin or minus 370 degrees Celsius, the function looks like a step function. The probability to occupy a state below the Fermi level is 100%, whereas the probability above the Fermi level is 0%. For higher temperatures, this distribution starts to broaden around the Fermi level. Around the Fermi level, the energy is distributed over values between 0 up to 1. The higher the temperature, the broader the distribution around the Fermi level will be. As you can see, for metal, the electrons are distributed in continuous electronic band, which is not fully filled. However, for semiconductors, this situation is different. The valence band is almost fully filled with electrons, whereas the conduction band only has very few electrons. The Fermi level is positioned in the forbidden band gap between the valence and conduction band. According to the Fermi-Dirac function, electrons have a 50% probability to occupy the electrode states at Fermi levels. Since no electronic band exists at this level in the forbidden gap, no electrons can occupy this level. So the real distribution of electrons over the 2 electronic bands becomes more complicated. In general, the Fermi-Dirac function shows that the energy levels in the conduction band have a low probability to be occupied, while the energy levels in the valence band have a high probability to be occupied. At absolute zero, a temperature of 0 Kelvin, all electrons fully occupy the valence band. The semiconductor material is not conductive. If you increase the temperature, the shape of the Fermi-Dirac function broadens around the Fermi level, and some electrons have the chance to occupy the conduction band as well. The higher the temperature, the more electrons can occupy the conduction band. This demonstrates the physical principle that if you heat up a semiconductor material, it becomes more conductive. Using the Fermi-Dirac function, you can tell something about the distribution of holes in the conduction band. The positions in the valence band at which the electrons are missing do recite the holes indicated by the blue dots again. 1 minus the Fermi-Dirac function shows for a semiconductor the probability that you will fill a hole at a certain energy level. This week we'll focus on the behavior of the charge carriers, electrons and holes in a semiconductor. We will use the semiconductor material silicon as an example, and in the next video lecture we will look how the charge carrier concentration in a silicon lattice can be manipulated using doping atoms. So see you in the next video lecture.